Good evening, everybody. Charles Dwyer is my name. I'm chairman of the Water and Environment Society here in Engineers Ireland. Thanks, everybody, for attending this evening's lecture, and for those of you online as well. So this evening's lecture is Tidal Energy Technology Development in Ireland, and tonight's presenters are Dr. Edward Fagan and James Donegan, just to be sure. All right. So I think the lecture will take about 40 minutes, and we'll have time for questions then afterwards if you want. All right. So thank you very much, guys. All right. And good luck with it.
Hi, everyone. Thanks, Charles. Yeah, my name's Edward Fagan. I suppose a bit of my history in tidal energy. I completed a PhD looking at the design of blades for turbines back in 2013, or started in 2013 until 2017, and worked as a postdoc in the research centre, part of the MaREI Research Centre based in NUI Galway. Right now I'm I've moved into wind energy, but using a lot of the same, I suppose, topics and expertise that I developed through tidal energy. So maybe a bit of an overview first on just what the MaREI Centre is. So MaREI is a research organisation. It's the national centre, the National Research Centre for Climate Science, renewable energy, and topics around the blue economy or the marine environment. It is an organisation with 12 partner institutions, so 12 of the higher education institutions around the country, and is over 200 researchers strong. And through the first phase and now into the second phase of the centre, there's been well over 50 industry partners. So what I'll talk about today is the academic side of tidal energy development, as well as the industrial side and some of the programs like the Marinette2 Transnational Access program that kind of bridges the gap between the two. So the MaREI Centre is broken down into a number of research areas. Research area 2 is on materials and structures. This is one of the underpinning sort of research areas that really helps develop enabling technology for all the different kind of scientific research as it's applied in industry. So we're looking at the materials and the structures that support wave energy devices, onshore and offshore wind turbines, tidal turbines, as well as kind of developing more into the bioenergy and the energy storage. So starting off with the energy generation side of things, but as the centre is developing, we're moving into topics that are closer and closer to, I suppose, the societal level and the actual application of energy throughout the full system. So a lot of the research is collaborative across all the different institutions in Ireland. So I have a number of case studies here to talk through. The first one is some material characterization work that was done between NUI Galway and UCD. So looking at how we can improve the mechanical performance and the cost effectiveness of materials for applications that really haven't been tested in before. So tidal turbines, you're talking about a device that has to operate for up to 20 years with limited opportunity for maintenance in really harsh conditions. So 20, 30 or 40 meters under down on the seafloor. You've got high pressures, and water ingress into the composite material is something that can happen and can have a really negative effect on the structural performance. So some of the testing or the material characterization work that's been done at NUIG was developing this pressure pot where they artificially aged the composite material, put it in seawater at high pressure, and watched the voids or the small holes in the composite material fill up with seawater. And then they did accelerated aging tests. So they did fatigue testing to see how the material performed when it was sort of simulated to have experienced 10, 15, 20 years of operation underwater. As well as this, then we're looking at the part of the centre in UCD is looking at different types of materials. So looking at 3D printing, fiber reinforced composites for use in new applications such as tidal turbines. The example shown here is additive manufacturing as part of the SFI iForm Centre and led by Professor Dennis Dowling in UCD. So this is 3D printing of fiber reinforced composites under different manufacturing conditions. So the top right picture shows the difference in the quality of the composite at room temperature as well as at under low pressure conditions. So you can see there's much less voids between the layers of the composite and therefore much better mechanical performance. So this kind of core materials level research is what underpins some of the structural design and structural testing research that I was a member of, or I was part of at NUI Galway. So taking in the characterization of different composite materials, looking at coatings such as hydrophobic coatings for reducing the adhesion of water and therefore the erosion on surfaces, and the surface treatment work at UCD. It's all pulled in together into coupon testing to look at how those materials behave mechanically, and then that feeds into our development of design and analysis software at the university. So I'll talk a little bit more about Blade Comp and the development of the software in a little bit, but for now I'd like to talk about the large structures test cell that we have at the university. So this is a full-scale structural testing facility. We have a modular steel frame attached to let me get this right, I think 10 by 4 meter or 10 by 6 meter reinforced concrete strong floor. So it's a modular setup. We can change around for the different types of tests or the different types of blades that we're testing. What we have here is a blade for 9 meter long blade for a tidal turbine. So we have 3 hydraulic actuators that are attached to a hydraulic ring main, and they can go up to 750 kilonewtons of force. So we do structural, static, and fatigue testing of different blades. The design analysis side of things, then, we, as part of, I suppose, the research that we do and the services that we offer, we also do finite element analysis, kind of assessments of the design of the structure, and analyze the model and analyze the actual test setups as well. So coming off the back of that and a couple of different research projects, we had developed this automated design methodology. So it takes in all the different input variables when you're looking at a blade, the geometry, the materials, the way they're laid up, the composite materials are laid up in a blade, and automatically generates these finite element models for different types of analysis. What we do then is take those models, and the software can output the kind of optimum design for manufacture. And working with Air Composites, so composites manufacturer based in Galway, we designed and built blades for 15 kilowatt wind turbines. So just to test the whole methodology. So these were tested in the lab. You can kind of see it. It's a little bit small on the right. So we did some mechanical testing of the blades to verify that the whole methodology and the software output accurate results. And we've done other physical testing, so it shows kind of modeling and testing of 13 meter wind turbine blades as well. One of the culminating, I suppose, points of this research was then a project, Horizon 2020 funded project called FlowTech. So that was working with Orbital Marine Power. They're a Scottish tidal turbine developer. They have they're building right now a 2 megawatt system. You can see it at the top right. So it's a floating structure with two 16 meter diameter rotors supported on it. So we used the Blade Comp software to to optimize for a number of different objectives the blade design. So we were looking at making a lightweight, high performance, and cost effective to manufacture blade. And using genetic algorithms, we were able to basically generate from the software thousands of different blade designs, assess them all against one another, and come up with the best design to be manufactured. So that project is ongoing. The blade is being manufactured at Air Composites right now, and I think testing is due to start in about June of this year. And this just gives us a little bit of an overview of the technology development programs in Tidal Energy since 2011 and the sort of inception of the lab at NUIG. Initially, we worked with marine current turbines. They were a Siemens-owned business at the time, but are now owned by Atlantis, or Simec Atlantis in the UK. So we developed a test specification for 8-meter long blades and acquired some of the hydraulic actuators for the initial testing. Following up from that, we worked with Open Hydro to test blades for their turbine. I think they were half-scale blades. That led into projects with Orbital Marine Power that I've discussed and Air Composites to test blades up to 13 meters in length. And sort of in parallel with all this was the development of the design software. And James will talk about it in a bit more detail, but we've also had projects working with ORPC to test blades for their turbine and kind of continuing developments into wind energy. So working with Air Composites and Suzlon, I think they're an Indian company. They're the biggest wind turbine manufacturer in India. And we're looking at testing blades with leading edge erosion resistant structures as part of another project. So that's kind of a summary of all the work that's going on in NUIG. As well as that, we don't just look at or as part of the MaREI Centre, we don't just look at the initial design side. We also look at operation and maintenance related research. So one of the groups led by Vikram Bakrashi in UCD has taken kind of through the low to mid-level TRLs technology for underwater image processing of underwater steel structures. So basically it is a system that takes images of different steel substructures and analyzes the levels of biofouling. So biofouling can increase the hydrodynamic drag on a structure, and part of that is actually being calculated. So the system basically can define which different types of biofouling is on a substructure and input them into finite element models where it can then output the resultant drag, and therefore you can do different analysis to figure out what the overall impact on the structural lifetime is based on levels of biofouling. So that's kind of an overview of the MaREI Centre side of the research. One thing that was sort of a big player in the research ongoing at NUIG over the last couple of years is the Marinette2 program. So Marinette2 is a Horizon 2020 funded research project. It is based out of UCC, and the whole goal of it is the standardization of all the different testing requirements for ocean renewable energy devices. As well as that, it's providing access to all of the different knowledge that's being generated in ocean renewable energy research, and providing access to different companies to kind of cross borders within Europe and avail of testing that's not available in their home countries. So the transnational access part of the program basically allows energy developers or device developers to go and use facilities in another country to test their devices free of charge, thereby supporting the industry. As well as that, there's some work packages around developing an e-infrastructure for this knowledge sharing and providing training to help kind of support the blue economy and create a highly trained workforce to support sort of the nascent industry. So the project started in 2017 and is going until 2021. This is the second of the MaRINET2 programs, 10.5 million total funding, 5 of which is going towards this transnational access, so paying for access for companies to use test facilities around Europe. And there's nearly 40 different companies participating from 13 different countries. So the 7 work packages in total, but you can see them at the bottom. The overall kind of topics they cover is standardization, e-infrastructure, training, communication, and then the transnational access. The team, who Michael O'Shea unfortunately couldn't be here today, so he passed his slides over to me, and Jimmy Murphy and Emma Knowles, all based out of UCC. And some of the the partners are listed here. So we've got EMEC, based out of Northern Scotland in Orkney, DTU in Denmark, and IFRMR, who we've worked closely with at NUIG on research programs. So the way transnational access works is there's 5 different calls over the 3 years of the program. The first call, you can see a good chunk of the money was paid out, 1.26 million, followed up by similar amounts in following calls. So there's still money left in the pot. If anyone here is a device developer or has contacts with them, they're welcome to put in for a proposal, what's really a relatively short proposal for the 5th call that's coming up later this year. And there'll be information sort of as part of webinar and FAQs on the application process. So every institution has an infrastructure manager that you can contact who will walk you through the process. So some of the statistics for Ireland so far are really quite good out of all the different participants. Nearly all of the applications to Irish institutions have passed, as well as, not just on the first call, but mostly on the first call and some on succeeding calls, with a total of over 300,000 of funding that's gone towards Irish developers and researchers over the first 3 calls. As well as this, there's a research project that has been coordinated by UCC called Tidal Turbine or Tidal Roundrobin. So basically to standardize all the different test facilities, the wave flumes or the flow tanks across across 5 different countries and 5 different test infrastructures. One tidal turbine has been developed. I think it's 1/10 scale, so about a 2-meter diameter, and it's being tested in each of the institutions. So you can see up to June of 2019, the turbine was tested in France, Scotland, and I don't know where CNR is based, but 3 different countries, and soon to be tested in Strathclyde and Queens. And the results are going to then be published as a comparison to show to help develop a testing standard for these devices. So the methodology is a 3-bladed tidal turbine, horizontal axis. The picture is shown in the test setup at IFRMR in Boulogne-sur-Mer in France, and it's basically subjected to a number of different flow conditions that are representative of regular and irregular waves, and the same acoustic Doppler velocimetry. So the same instrumentation is used to monitor the device across all the different infrastructures. So one of the big successes of the project, as well, is this development of a virtual access sort of database that all of the different research is after each developer basically tests at an infrastructure, they produce a report. It goes onto this virtual database and is fully accessible to researchers and developers across around the world, and it's in line with the European Commission's ideas around open research and development for kind of publicly funded research. And just one last image of one of the successful projects was Shuttle Hydro. They're a company based in Germany, and they have I think it's a maybe 6-meter diameter turbine that they're installing in the Bay of Fundy in Canada, and they were successful in the Transnational Access Call 3 as well as Call 4 to do static and fatigue testing at our facility in Galway. So I thought we'd get one last little plug in. And right, that's it. Thanks very much.
And thanks, Charles and Engineers Ireland, for inviting us here tonight to talk about tidal and, in our case, river energy also. My name is James Donegan. I'm the Director of European Operations and Lead Electrical Engineer for Ocean Renewable Power Company, also known as ORPC. Some background on ORPC. We're a US company. We're headquartered in Portland, Maine, which is about 2 hours north of Boston. We were founded in 2004. We have about 30 employees, most of which are located in the US. We also have offices in Quebec in Canada and in Dublin in Ireland. To date, we've raised over €73 million with about 50-50 split between private investment and from federal and state government grants, both in the US and in Ireland. And we're the only company in the world to have delivered power to a grid from both tidal and river marine energy projects. So I figured I'd start tonight. It's usually we talk to people in the tidal energy community, so kind of go back to basics and list off kind of why it is an industry in the first place. As it's Engineers Ireland, I figured I had to put in some formulas. So this is the formula for how much power you can extract from a turbine in an open flow. So this is the same formula that wind turbine developers would use to design their turbines, and it's tidal and river energy. It's essentially underwater wind turbines. So kind of why tidal energy is such an exciting environment to be in is, if we look here using this formula for how much power you can extract from a wind turbine, we base it on the most common wind turbine in the world, which is a Vestas V90. We plug in all the details for that turbine, you get 2 megawatts out of it. And that's based on a maximum design wind speed of 25 meters per second. If you put that same turbine underwater and have a water speed of 3.5 meters per second, which is much lower, but that's typically what the max design water speed is for tidal developers, you get an output power of 56 megawatts. So you're talking 28 times power increase, which is huge. So what that enables us to do is we're able to put much smaller turbines in the water. So if you look over on the kind of right hand side here, we're able to reduce the area of the turbine down to like a 20 by 10 system, which is minute in comparison to some of the large megawatt scale wind turbines out there, but we're able to get the same power out. So that's one big reason why tidal energy is definitely going to be part of the kind of future of renewable energy. And another reason is, if we look here in the past 60 years or so, 70 years of wind data in Dublin Airport, there's no real trend that you can pull out of it. It's purely weather based. We don't know, we can't tell you how much wind is going to be produced. So there's no real way of knowing what the impact to the kind of national grid, utility grid, is going to be from a wind site. That's the opposite with tides. So one of our sites in Eastport, Maine, where we deployed a system in 2012, it's green dot up here, right on the border of the US and Canada. These are measurements taken over a 30-day window. I think these measurements were taken back in 2013, when just after the system was installed there. And you can see it's a purely sinusoidal pattern. It has peaks and flows based on the kind of the lunar pattern for each month. So you have peaks and you have troughs of your peaks of the sinusoidal waveform, but ultimately it's entirely predictable. So these are some measurements that we took from that site in blue, and we also have our predicted water speeds in red. So they're pretty bang on the money. And so much so that we can tell you, today, January 15, 2020, these are what the speeds are at that site. And this is not for measurements. We're able to we have a MATLAB program which outputs it for us. And we can tell you in 10 years' time, these are the water speeds that are going to be at that site. So that's the kind of impact tidal energy can make. We can be a base load energy source for utility grids because of how predictable the energy source is. We've installed 12, our company has installed 12 projects since 2004. The kind of main, the first of which that was grid connected was in 2012, which is this TIGEN system. So ORPC has developed kind of a modular turbine design where we have a single turbine size, and if we want more power, we just attach more turbines to that driveline. And it's designed. We chose this cross-flow turbine design, which is like an old-fashioned lawnmower as opposed to the more conventional wind turbines that people see, because we can access more sites through this method because it has a much lower profile. So we're able to sit in lower depth sites which a more conventional wind turbine, let's say, would not be able to fit. So this is the TIGEN system, which was grid connected in 2012, and there were some flaws with this system in what the foundation was. So we had piled foundation, 10 piles drilled into the seafloor. That was a very expensive undertaking, and ultimately we're trying to make a commercial product, so that we're constantly, every deployment that we have, we're learning new ways that reduce cost, improve efficiency. So in 2014, we tested out a prototype for our tidal systems, which was using a buoyant tension mooring system, which is essentially using a buoyancy tube, which is a tube filled with air, and then putting our turbines onto that, and then using gravity-based anchors to kind of lower the system down. So essentially the turbine is floating in the middle of the water column, which has benefits because it's a much quicker installation. You can just do this, and we installed this system in 15 minutes using a catamaran and winches. And also we're able to access higher water speeds because you're not operating on the sea floor. You can just increase your mooring lines, and you can access the higher water speeds, which are closer to the surface. And then we also have our RivGen technology, which is essentially the exact same as the TIGEN system operation-wise, but it's for river sites. And that's pictured here, this was the first grid-connected system in 2015. And I have a video on the next slide, which I guess I can't play on PDF, so we'll just explain how we install this. We were able to float a RivGen out to its system, hook it up to its anchors, and then it's sitting on two air-filled pontoons, and we essentially just fill one pontoon with water. That side sinks to the bottom, and then we fill the other pontoon with water, and then that side sinks to the bottom. So it's, our business development people like to call it a self-installing turbine, but our field crew don't like that as much because they're putting in the long hours. So this was a video of the system being installed over a time lapse. And then this is the kind of commercial RivGen system, which was installed in the summer of last year. So it's rated for 35 kilowatts at 2.25 meters per second, which is kind of the nominal water speed that we see. We try to base all our sites off, but it's capable of operating up to 80 kilowatts at 3.5 meters per second sites, which are kind of the maximum power sites that the system is designed for. The idea behind this system is that it's to go to remote communities to offset the cost of diesel energy. So there's in northern Canada and in Alaska, many places in the Arctic, there are thousands of remote communities which fly in their diesel by plane to then operate diesel generators incredibly inefficiently to get their electricity because they're not connected up to a national grid. So they're paying electricity prices about €1 a kilowatt hour, which, in Ireland we're paying 15 cents a kilowatt hour. Some places in the States you're paying 9 cents a kilowatt hour. So they're paying over 10 times what people on a national utility grid are paying. So kind of because the tidal and river energy technologies are still in their infancy, this is an area for a developer where we can develop and manufacture systems and sell them to kind of gain the knowledge and improve the efficiency of the system and eventually drive down the costs. And then this is the kind of next generation tidal system. Again, this is designed for remote community tidal sites. And this kind of operates up to 350 kilowatts, and it's the same kind of floating buoyancy pod design that I was speaking about earlier. And this is kind of mentioning why ORPC is looking at remote communities as a market, and it's because their electricity is 10 to 15 times higher, and there's thousands of these markets around the world, kind of percentage electrified markets or electrified grids are outlined here globally. Where we're focusing our attention on at the moment is in the Arctic region, where each red dot here is a community that operates on a remote grid. So this is kind of ORPC's early adopter market, and again, this is just talking about how many millions of gallons of diesel are burned. So this is both a cost and a huge environmental impact, which ORPC can offset. And these are some of the advantages of our system. So I spoke about earlier, kind of the idea behind our RivGen system in particular is that it's designed to be low cost and modular, and it can be shipped anywhere in the world. And that's the whole design restrictions that we've placed on ourselves, is that it has to fit into four standard shipping containers. So one for each pontoon, one for the turbine and generator, and then one for all of the additional parts, such as anchoring. And then those can just be put on a barge and shipped anywhere in the world. This is the image on the lower right here is what I was speaking about earlier about why we've chosen this kind of cross-flow design. Some of the images that Ed showed earlier, there was surface-mounted devices which companies like Orbital and Marine use, and those have a kind of a visible and environmental impact because they're breaching the surface and they have to account for waves also. And then with the kind of more standard kind of axial flow turbine, which is in the center here, again, those can't access the shallower sites, so you're limiting the amount of sites that your turbine can actually reach. And then also some other benefits are, every new site that ORPC goes to, the local fishing community they require us, before we can get a license to install, they require us to have a lot of monitoring on our systems. An example of that is in Igiugig, Alaska, which is where our RivGen is installed. That's the home of the largest sockeye salmon run in the world. So in 2015, the week we were installing, there was 600,000 salmon swimming upstream in the same river. So there's a picture of one of those salmon up here. And what we've seen, we've the turbines kitted out with cameras, with Doppler sensors, and essentially the salmon want to swim in the slowest parts of the river because they're swimming upstream. It's easier for them. And also the turbine, when it's operating, it's creating a pressure wall in the channel. So the same way a fish isn't going to swim into a wall, it senses a pressure boundary upstream and simply swims around the turbine. So why is marine renewable energy not mainstream? Because I've just been talking about how great it is, and it all comes down to cost, basically. So the levelized cost of energy is the metric that these technologies are based on, and that's how much does it cost to generate a kilowatt hour of energy. And this is still higher than kind of what our baseline target is we want to be a competitor for offshore wind. And it's still higher than that, and we have high capex costs. That's due to economies of scale, basically, because we're a new industry. We've a handful of installations as opposed to installing farms of these where we can put in an order for 100 turbines. It's one-off systems that we're installing. And also we have high operational costs because, if something were to go wrong in the gearbox of a wind turbine, you send up a technician, which takes, half an hour. They can have a look. Whereas these systems are installed underwater, and we've designed the systems to operate for 20-year lifetimes, but there's a lack of extended operational runtime. So there's no way of us knowing whether, even though it has been designed for 20 years, is it capable of doing that? So there's that lack of runtime, which essentially increases our operational costs. So kind of why we're here tonight is Tidal Energy Technology in Ireland. So why does ORPC, US company, have an office in Ireland? So a big reason is, if you're a tidal energy company, you need to have presence in Europe, because this is where a majority of the tidal resource is in the world. And also, Europe has very friendly kind of government schemes to help foster companies like ourselves through technology development, which isn't necessarily the same in other countries, which is why it's been also beneficial to operate in Europe. So ORPC Ireland, we set up the company in 2015. I was previously working with the company in the US, doing a lot of field work, and then moved back home in 2015. And we've been successful in getting some funding from Sustainable Energy Authority of Ireland, as well as the European Commission. So far, we've had 4 projects here, kind of ranging from smaller scale resource assessment work in Donegal to see what the tidal resource is there, up towards kind of large scale R&D efforts to develop new turbine and generator technologies. And those have been funded through Horizon 2020, Ocean Renewable, and SEAI as well. Some of our research partners, we work a lot with UCC, NUI Letterkenny Institute of Technology, as well as Fraunhofer Research Institute in Germany. And then some of our industry partners, Air Composites, who Ed mentioned, they're our manufacturer for our turbines, which kind of was a new relationship that we built since opening the office in Ireland. And we also have IKM Electro, which are a developer of our generator, Black & Veatch, who've done some resource assessment for us, SKF, and Sustainable Marine Energy. So I mentioned the tidal resource that exists in Europe. So the total extractable resource globally is 160 terawatt hours per year, and 40% of that is in Europe, and about half of that again is in just the UK. So being close to the UK, and for obvious Brexit reasons, not being in the UK is beneficial. And these are some examples of sites that we've investigated. There's 80 sites up on the screen here, and again, kind of what we're looking at this early stage is kind of early adopter markets. So similar to the markets I spoke about earlier, which are places which are spending a lot of money on their electricity, but also looking at the kind of market that 5 years time, when we've sold enough of these turbines to the remote communities to develop the technology enough where it's competitive with offshore wind, where are the big tidal sites that we can install an array of these? And that's kind of some of the work that we're doing in Ireland at the moment. We've also managed to get some funding to support our turbine design. So our kind of primary office for computational fluid dynamics work is here in Dublin, just on Bagot Street, actually, 10-minute walk from here. So we've performed CFD analysis, which this is the basis for how we size the entire system. So the idea behind this is that we can, without installing the system into water, which is a very expensive undertaking, we run these 2D and 3D computational fluid dynamics simulations, which also is actually surprisingly an expensive undertaking as well. And we're able to understand what the best arrangement for the turbine is, like how many foils should we have. We call them foils instead of blades. It sounds less menacing for the fish. And how many foils should we have, what the joint should look like, what operational speed is this going to rotate at for a given water speed. And that all kind of affects what the mechanical design of the larger system is. So this is kind of a very early stage design for like what the next system is going to look like, and that feeds into every other design choice that we make. Turbine manufacturing, I mentioned that we work with Air Composites in Galway. They manufactured our turbines for the RivGen system, which is now installed in Alaska. this is the system here just before it was shipped out last May. And then the test facility at NUIG that Ed mentioned, we're currently testing a new joint design at that facility at the moment. Kind of one of the negatives about when this system is actually operating is that it's difficult to get actual operational data from the foil, like stresses and strains and forces acting on the foil, back to our SCADA system because it's a rotating system. So this is a way of kind of us verifying our FEA analysis and our design work through an actual lab setting where we're able to input the same loads that we will see based on our CFD analysis and see how it affects the turbine and the joints. And then I also mentioned that this is where we're doing our generator design and manufacturing. We work with IKM Electro in Norway, and one of the kind of our learning lessons through our many installations has been you need to make the system that's underwater as stupid as possible, because if putting stuff underwater it's asking to be broken, so everything needs to be very simple. So that's why we use a permanent magnet generator. We don't have any gearbox, and through this Horizon 2020 funded project TIDA, we're designing and testing a fully encapsulated generator. So instead of having a kind of exposed stator and rotor, which if seawater were to leak into the generator, it would completely catastrophically destroy the generator, so it can't be used further. This system is designed for seawater in the air gap, kind of under normal operational as a normal operating case. And as well as that, we've designed a cantilevered bearing design. So we've reduced the number of bearings from 2 down to 1. So we're just constantly trying to reduce the amount of failure points underwater, and that's because these systems are designed for as minimal maintenance as possible and for operation up to 20 years. And that's my presentation. So thanks very much. If you have any questions, let me know.
Did you talk about how the tidal ocean turbines are anchored?
I didn't. For our tidal system, it depends on the geotechnical data for each site. But what we've installed in the past has been like pile-driven anchors that we've used, and we've also used gravity-based anchors. And we're looking at rock pile anchors at the moment as well. We're working with sustainable marine energy based in Scotland to develop a rock anchor design for our system.
Yeah, it varies between the different companies, the approach taken. The company we're working with right now, Orbital Marine Power, have a floating platform and tension leg connections down to the seabed. So they're, I think it is probably piles to connect the tension leg down on at each point. But yeah, it varies company to company and what approach they go for.
You mentioned extractable tidal energy and why Europe, particularly the UK, has so much. What gives the coastline extractable tidal energy?
So essentially, you've a huge body of water in the Atlantic Ocean, and for each tidal cycle, that body of water kind of, when you have high tide and low tide, the water has to come from somewhere, and the Bay of Fundy, which is the channel of water between the US and Nova Scotia, that has some of the biggest tides in the world because the whole Atlantic being funneled through that channel. And similarly in Europe and kind of the Northwest Europe, you have that entire Atlantic Ocean kind of funneling through, France and the UK. That's a huge, there's excellent tidal resource there. Off Northern Ireland, when it's being funneled through kind of Scotland and Northern Ireland, that's some of the fastest tides in the world. And similarly in the Orkneys, off the coast of Scotland, those are some of the largest tides. So that's kind of where you look for, is where is there a large body of water that suddenly has to be funneled through a smaller channel.
What's the cost of building one of these?
So the cost, it's kind of very variable based on what the site actually, what the water speeds are. Obviously, if it's a very fast river site, for example, at 3.5 meters per second, the cost of that is much lower because everything's measured on levelized cost of energy, and that system pays for itself quite quickly. Whereas it's, we kind of say in our sites now, 2 meters per second is kind of the threshold for when it makes kind of commercial sense, but it's variable based on the site.
And what's the percentage for the energy production compared to especially wind energy? And is there from a government side, like, are they funding it to increase it?
To increase
to provide the electricity to the energy production.
Yeah, so there's some kind of schemes that governments have. I mentioned it back here. So like the German government gives subsidies for marine renewable energy. It's not the greatest country in the world for tidal power. It doesn't have much of a coastline. But it does give subsidies of 25 cents per kilowatt hour, and it has relatively high electricity prices. So if we were to install a system there, then we'd be able to sell that power for 50 cents a kilowatt hour, which is actually that's right about where our LCOE is anyway. Whereas if we were to go to a country without that kind of subsidies, it's not really competitive with the other generation that's on the grid.
Do you know how much percentage of Ireland is provided from the tidal energy?
There is no grid connected tidal system in Ireland.
So in Northern Ireland, in Strangford Lough, there was the marine current turbines. They had a turbine installed there from 2008 until maybe 2016. It was a test device though, so it was grid connected, but yeah, it was mostly used as just to test their system and their operation and all the rest. So it wasn't really supplying electricity onto the Irish network. The one big source of funding that's just been announced recently was through the Interregional Development Fund. So it's a European industry funding program. I think it's 23 million. Do you know the Tiger program?
I do not know.
Okay, right. Yeah, it's something like 23 million is funding a consortium of companies that are looking to develop tidal energy. So it's not just developers, it's sort of supply chain companies. The idea there is that it helps build up an industry and a greater supply chain for one or two developers that all the other developers then benefit from. So there is kind of more funding going into it now than I think there was even a few years ago. And the goal is to have a European-based tidal energy industry, I think, in the next 10 or 20 years.
I hate to say this, that might be wrong, but I hate to say this, that in terms of efficiency, marine energy was less efficient in terms of production of energy. And another thing I wanted to ask is, in terms of transport between the turbine and the populations going to serve, are you also investigating that part, or is it more related only to the production itself?
Are we also investigating the transport?
So how the electricity goes from the turbine into the population?
Sure.
It's also a lot of energy.
Yeah, absolutely. And the kind of, I suppose, the efficiency question, the published efficiency of the V90, the Vestas V90 wind turbine is 40%. Our RivGen system, we've measured that as being 36% efficient. That's without again, I mentioned our system is as dumb as possible, so there's no active pitch control. It doesn't care what direction the water comes from, whereas wind turbines, they have active pitch control on their blades and they've yaw control to make sure that they're facing right into the highest wind speed. So that's likely a reason for that reduction in power, but there's no physical reason for a reduction in efficiency when you install it underwater. And then for the grid infrastructure, that is actually a problem in many of these areas that we're going into, because a lot of these sites that we're operating in, they're very remote regions which have pretty sparse populations. So their grid has been designed to kind of feed from a centralized power plant down. So their electricity lines are designed to operate in one direction and feed X amount of people. Whereas if we were to put an array of turbines in there, all of a sudden we're putting in much more power than that town or village would consume, and we're sending it in the opposite direction. So there's definite grid infrastructure issues, and we saw that problem in 2012 with our Tigen system. We had to install new electricity lines to our site because the the original ones weren't capable of handling the amount of power we were producing.
And what's the, if it's commercially viable, the turbines within rivers and tidal, what's the biggest barrier here that we don't have them dotted around the place at this stage? It's still not.
So like we see our RivGen system as being commercially viable. We're able to produce power at a reduced cost versus what people are paying in these remote communities now anyway.
But even I'm just saying built up areas of obviously I'm from Cork, so
yeah.
Stick it in the lead. It's close to the population. What's the, is it
so I mean it's
environmental, is it?
There's definitely like environmental and getting permits to install a system. That's not something that take weeks or months. That's years of planning to get that in place. Yeah. And that's just because it's such a new industry that there's not a.
Is that a fear factor thing? Is it?
There, I mean, you kind of have to jump in with both feet, like in a lot of these places where you can't. You have to, and that's why we've done such a tidal resource in Europe. Where are the sites that we can go to, and install something, in 3 years' time. And we have to start that process now, engage with the local community and kind of begin that planning process. Because we don't know what the hurdles are, because the permitting process is different in every country. And for example, there's like places like the Channel Islands, which have an excellent tidal resource, and that's technically not part of the UK, so it's not governed by UK law. So again, if the UK were to have a formal permitting process, which it doesn't for installing tidal projects, where do the Channel Islands fall in that? So it's every new site that you look at, there's a different set of barriers that you come up against. And then like ultimately cost is a huge one as well, that these systems are very expensive to manufacture. And the RivGen system that we build is designed so that as inexpensively as possible, because ultimately in a river, and because of how we install and retrieve the system, it's a quick operation. It takes 20 minutes. It uses local fishing vessels, so that's not a huge deal. If something goes wrong, and things have gone wrong, and we've sent out a boat to like lift it to the surface, send out a technician to look at things, and that's kind of suitable for that scale of system. But if you're talking about a tidal system then deployed 100 meters underwater, it's a much more expensive undertaking. So you have to kind of over design everything to make it suitable for long-term deployments. I mentioned wind turbines, you can send up a technician to fix a gearbox, whereas we don't use gearboxes because it's a component of the drivetrain which does break more frequently than others. And that decision meant that we had to build a permanent magnet generator, which is it's much more expensive generator than the alternative. So it's kind of a lot of design decisions that ultimately need to be made to operate long term. But because of the economies of scale, you're building one-off systems, and you're not able to, we don't have a back order of 100 of these, because the industry just hasn't picked up. You need systems operating for 5 years consistently to be able to point to a possible client or customer and say, this is a working system that you can purchase. So it's it's a pre-commercial phase is what we call it. And it's
to add to that, the near the Orkneys that James mentioned in northern Scotland, there's a test center called EMEC, and that's basically a section of the ocean that's been permitted for developing kind of up to full scale and multiple tidal turbines. So a few different companies have, including Open Hydro, who were at one point the biggest developer of tidal turbines. We're an Irish company. Them and others have put turbines in this specific test center, and I think last year, 9 gigawatt hours of power were generated and put onto the grid. So the development process in the UK has been quite good. There has been funding to support developers to put devices in a specific area, show that they're generating power, go through the process that you're talking about of showing that you have devices there working for years. In Ireland, the planning process and the permitting process for putting any devices, even offshore wind turbines, is not quite in place yet. I'm not a policy expert, so I'm not going to talk too much about that. But I know there's plans in place to allow development of, or allow developers to put devices in Irish waters at some point in the future. It's just they can't get permits right now.
When you say that the system is designed for 20 years, does it mean that after 20 years, the whole system needs to be replaced, parts of the system? Because I mean, you can't really do maintenance.
Sure, it's I suppose that 20-year lifespan is something that we go to, for example, our bearing manufacturer, which is SKF, and we tell them, we want the system, we want these bearings to last for 20 years, and these are the same bearings, the ones we use in our generator are the same bearings that are used on the wheels of trucks. So like they know how long those bearings are going to last for. They've a huge test facility there, so they're like, yeah, that will last for 20 years under these loads. Whereas if we had said, it needs to operate for 50 years, then the size of those bearings increase, and how you lubricate those bearings, that's a more expensive undertaking. Whereas our systems are designed so that every year, for a RivGen system, every year there's a scheduled maintenance cycle, which unfortunately for our company, a lot of the sites are in pretty cold climates, whereas like wave developers get to go to Hawaii and Portugal. We're camped out in Alaska and northern Canada. But in one of our sites in Alaska, every March the upstream lake, the ice kind of breaks up and floats down river. So that's a concern of ours that that could impact the system. And again, because the system is in its infancy, so we don't quite know what that process is. So how we're approaching that is, for while the ice is breaking up, that kind of 2-week window, that's when our maintenance is going to happen, and that kind of will lift up the system, bring it to shore, essentially perform visual checks on the system right now, because it's kitted out with hundreds of sensors. We already know what's happening. It's and everything is designed for that 20-year lifespan, but it's more of a visual check and then reinstall it and make sure it's operating okay.
Thanks, guys. Thanks, James, and thanks, Edward. Just before you finish, there's a thank you there from Engineers Ireland for coming and presenting as well.
Oh, great. Thank you very much.
Cheers. We have to buy these books, you thank you very much, guys. Yeah, you might put your hands together for them. Just before you finish, thanks for coming tonight, everybody, as well. And right on cue, lads, in fairness to you. Just before we finish, there's 2 events I'd like to mention. Our next event is on pressure management, and it's on the 5th of February in this lecture theatre. And it's with, we've represented from Irish Water, and we have Breffney Conroy as well coming from Water Control, based out in Dublin. And the other one then is with CWEM. It's health through water, I suppose. Perfect timing in terms of the various boil water notices in the past, recent past. A study of the need for and provision of healthy water supply post, present and future. That's on the 28th of January in the Maldron Hotel in Pierce Street. So that's through CWEM. You don't need to book it or anything. You can just turn up on the night. Okay, so thank you very much, everybody, and have a good evening. Cheers.